Hi class, today we're going to start section 4.6, which is with modeling with exponential functions. So we're going to look at several different types of models in this section and run through examples of them. So our first model is exponential growth, where we're looking at the doubling time. So this idea comes from biology. So suppose we start with a single bacterium. Which divides every hour. After 1 hour, we would have 2 bacteria. After 2 hours, we would have 4. Three hours, 8 bacteria, and so on. So we can see the bacteria population after T hours is modeled by f of t equals 2 raised to the t. So we can adjust this base model to fit other more specific models. So I'm going to give us the formula: exponential growth, or the doubling time formula. So if the initial size of the population is n naught, and the doubling time is a, and the doubling time is the time it takes for the population to double, then the size of the population at time t is n of t equals n naught, our initial population size, times 2 raised to the t over a, where a is our doubling time, where a and t are measured in the same units. So if we're looking at hours, then both t and a need to be hours. If we're looking at days or years, they have to be with the same measure of time unit. So now we're going to look at an example. So we're going to look at bacteria population. So under ideal conditions, a certain bacteria doubles every half hour. initially, there are 1,000 bacteria in a colony, or in our colony. Okay, so first we're going to find a model. After T hours. Oops. And second, we're going to find how many bacteria are there after 4 hours. And then third, after how many hours, so we're going to find the time, will the bacteria reach 1 million? So let's start with finding our model in part A. So we know that our base formula NT equals N naught times 2T over A. So here we have N naught equals 1,000. And we know that our A is every half hour, or 1/2. So N naught is 1,000 and A is 1/2. So now we can write out our actual formula as N of T equals 1,000 times 2, and then if we do 1/2, 1 over 1/2, we just get 2 out, so we get 2 raised to the 2t power. So that is our equation, and so now we're going to look at part B, which is after 4 hours, so time equals 4, so that means that we have N4 equals 1,000 times 2 times 4, which is 1,000, 2 to the 8th. So then if we were to multiply everything out, we would get 256,000. So after 4 hours, that's how many bacteria we would have. And now for C, we want to see when we will get 1 million from our equation. So we're going to solve for T. So first we're going to divide by 1,000. So that will give us 1,000 back. You can see 3 zeros here, cancels 3 zeros over here. So we end up with 1,000 equals 2 raised 2 to the T. So now we're going to first we're going to exponentiate both sides. And I'm going to exponentiate both sides in terms of log base 10 because we have this 1,000 over here, so that'll make it kind of clean. So log 10 of 1,000 equals log 10 of 2 to T. So then this just becomes 3 because we have 3 zeros. And now we can bring the exponents down and we get 2T log of 2. And now we divide both sides by 2. So we get 3/2 equals T log of 2. And now we divide both sides by log of 2. So then we have T equals 3 over 2 log 2. And this is approximately 4.98 hours. So it'll take about 5 hours for our population to reach 1 million. Okay, So now we're going to move on to another example of this type. So this is looking at rabbit population. So a certain breed of rabbit was introduced onto a small island 8 months ago. The current population is 4,100 and doubling every 3 months. Okay, so first we're going to find the initial population. And then we're going to estimate the population after year 1. Wait, after 1 year, sorry. After being introduced. Okay, so in order to do this estimation, we will eventually need to develop our model, but our first step is going to be finding the initial population. So we know that our base model, N of t, so that we're after this N naught, 2, and then since their doubling time is 3 months, that means that our A is 3. And we know, so this is what we have to work with, and we also know that N of 8 is 4,100. So this also is equal to N naught 2 8/3. So now we're going to solve for N naught. So our first step is going to be, we're going to divide 410 by 2 raised to the 8/3. So we have 4 over 2 raised to the 8/3 equals N naught. And then when you plug this into a calculator, we figure out that it is N naught is approximately 645. So this is what we're going to use in our model. Okay, so now for part B, so we can write out our model. It's NT equals 645 times 2t over 3. So now we're going to look at 1 year, which means that t equals 12 because we're measuring everything in months. So N of 12 is 645 times 2 raised to the 12 over 3. So this gives us 645, 2 to the 4th. And so then multiplying this out, we will get 10,320. So after about 12 months, there would be this many rabbits. Okay, so now we're going to move on to a different type of exponential growth. we're going to look at exponential growth with a relative growth rate. So a population that experiences exponential growth increases according to this following model. So the looks like n sub t equals n naught e to the rt. You might think that this looks very familiar because it looks almost identical to our continuously compounding interest formula, except instead of a p, we have an n naught. But it's a very, very similar idea. And so where n naught is the population, nt, is the population at time t, and naught is the initial population. R is the relative rate of growth, and it's expressed as a proportion of the population, and t is time. So we're going to look at an example, and this is predicting the size of a population. So the initial bacterium in a culture is 500. Biologists make a sample count and find the relative growth rate is 40% per hour. So first we're going to find a model. Then we're going to estimate the count after 8 hours. And then we're going to find how many hours it will take for the bacteria count to reach 100,000. So first, in part A, we need to create our model. We can note that our n naught is 500. Our R is 0.4 since it's 40%, and T is measured in hours. So putting this all together with this formula up here, we will get n of t equals 500 e to the 0.4 t. So now when time equals 8, we're going to see that n of 8 is 500 e to the 0.4 times 8, which when you evaluate with a calculator is approximately 12,266.27. So after 8 hours, we'll have approximately 12,266 bacterium. And then part C, we want to solve for T when we have 100,000 bacterium. So first step, we're going to divide each side by 500. So we're going to end up with 200 equals e to the 0.4t. And now we're going to take the natural log of both sides. And now we're going to divide both sides by 0.4. And then plugging this into a calculator, we see that t is approximately 13.25 hours. If we had in-person classes after each one of these examples, I'd normally be asking y'all if you had any questions and clarify things. So if any of these examples that I'm doing, if y'all have questions on them, please come to my office hours and I can help explain them better. It's hard to try to answer questions I don't know about when y'all aren't in front of me. But from here, we're going to move on to another type of model, which is radioactive decay. So radioactive materials decay by emitting radiation. The rate of decay is related to the mass of the substance physicists express the rates of decay in a term called half-life. And so half-life is the time it takes for a substance to decay to half of its original mass. So in general, for radioactive substances with initial mass m naught and half-life h, the amount of mass remaining at time t is modeled by m of t equals m naught times 2 to the negative t over h. So the reason that we have a negative number is because our mass is decreasing, it's getting smaller. So we express that with a negative exponent. So we need to solve for our relative decay rate R, since this is going to become, so we like to use this model in the form of with exponentials. So I'll skip a step. Express this model in the form m naught e to the minus rt. We need to solve for r. In terms of half-life. So if we look at m of t equals m naught e to the minus rt. So if we want to find when our mass is half of our initial mass, that means our output is going to be m naught over 2 equals e to the minus rt. Oh, and then t would be the time it takes for it becomes h, which is how long it takes for us to get to our half-life. So here, m of h equals m naught over 2 when t equals h. So we can divide both sides. Oh, whoops, there should still be an m naught over here. That didn't go away. So now we're going to divide m naught from both sides. So we end up with 1/2 equals e to the minus rh. And now we can take the natural log of both sides. And now we're going to divide both sides by negative h. And I'm going to take this negative sign over here, draw it a little taller. And I'm going to bring it inside the logarithm so that I can rewrite this as r equals the natural log of 2 over h. Instead of 1/2, because it's always nicer to have whole numbers than, it's always better to have whole numbers than fractions. So, radioactive decay model with E is m of t equals m naught e to the minus rt, with r equals the natural log of 2 over h. So now we're going to do an example with radioactive decay. And note that we'll need to use both the m naught e to the negative rt as well as our, oh, where is it? Up here. Our mt equals m naught times 2 to the negative t over h. We'll need to use both of these equations in a lot of problems because they're essentially the same equation, just expressed different ways, and both ones have their uses. So we're going to look at something called polonium 210, which is often expressed as 210 PO. And this has a half-life of 140 days. So suppose a sample of this has mass of 300 milligrams. So our first step is find a function that looks like m of t equals m naught 2 to the negative t over h that models the mass after t days. And then second, we're going to find a function that looks like m of t equals m naught e to the minus rt that models mass after t days. So, and then we're going to find the mass remaining after 1 year. And we're going to find how long will it take for the sample to decay to a mass of 200 milligrams. Yeah, milligrams. I'm bad with units. I haven't taken a science class in a really long time. Okay. So A, we know that our m naught is 300 and our half-life is 140. So that means we can't, and our time is measured in days. So that means that m of t is 300 times 2 to the negative t over 140. And then for B, we know that m naught is 300 and r is the natural log of 2 over 140, which is approximately negative 0.005. So the amount, our equation will be modeled by 300 e to the negative 0.005 t. So for C, we want to look at 1 year, which means that t is 365 days. So our mass of 365, I'm going to use the equation in part A. So I'm going to look at 2 to the negative 365 over 140. And I could have picked the other equation. I'm just demonstrating that you can use both, because in part D, I'm going to use the equation in part B. So solving with a calculator, this is approximately, not exactly equal, but approximately 49 days and 256. I'm sorry, milligrams, not days. So after 1 year, it will be approximately 49 milligrams. So now looking at D, we want to look at when MT equals 200. And we're going to use the equation with E. And this time we're going to solve for T. So first we're going to divide both sides by 300. And now we're going to take the natural log of both sides. And now we're going to divide both sides by negative 0.005. So plugging this into a calculator, we see that T is approximately 81.9 days. So it'll take about 82 days for the mass to become 200. All right, we are moving on to our last model type, and it is Newton's law of cooling. So if D naught is the initial temperature difference between an object and its surroundings, and if its surroundings have temperature Ts, then the temperature of the object at time t is modeled by T of T equals the temperature of the surroundings plus the initial difference times e to the negative kt, where k is a positive constant of the type of object. So k is determined by what object we're looking at. And so this equation, what it's meaning is if you take something that has an object that's a different temperature than like the air around it or maybe the water around it, then it will try to go towards the temperature here. It'll approach the temperature of the surroundings. So if you have a really hot item, it cools down if it's in a cold room, versus if you have a really like a cold beverage and it's a hot summer day, eventually that beverage will become room temperature. So this model, it models that behavior. So we're going to look at an example. And this is on a cup of coffee. So a cup of coffee has temperature 200 degrees Fahrenheit, and it is placed in a room with temperature 70 degrees Fahrenheit. After 10 minutes, the temperature of the coffee is 150 degrees Fahrenheit. So first, we're going to find a function that models temp. The temperature of the coffee at time t, and then b, we're going to Find the temperature after 15 minutes. And then we're going to see how long will the coffee have. I'm sorry, this sentence is, okay. How long will it take the coffee to cool to 100 degrees Fahrenheit? So starting with A, we need to find our model. Well, we know that we have, this is our initial formula. So, and we know that T of S is 7 degrees Fahrenheit. So we need to, first off, find K. Oh, I'm sorry. First, we need to find the difference in temperature at the initial point. So D naught is the temperature of the coffee, 200 degrees, minus the temperature in the room, 70 degrees. So this becomes 130 degrees Fahrenheit. So that means we've gotten to T of T equals 70 plus 130 e to the minus kt. So now we must find K. So we know that after 10 minutes that the coffee is 150 degrees. So that means we have 70 plus 130 e to the negative k times 10. So if we divide 70 from both sides, we end up with 80 equals 130 e to the minus 10k. Now we're going to divide both sides by 130. So we end up with 8 over 13 equals e to the minus 10k. And now we're going to take the natural log of both sides. And now we're going to divide both sides by negative 10. So we end up with k equals negative the natural log of 8/13 over 10. So plugging this into a calculator, we find that it is approximately 0.04855. So that means our model is T of T equals 70 plus 130 e to the minus 0.04855 t. So now we're going to move on to B, which was we're going to find the temperature after 15 minutes. So T of 15 equals 70 plus 130 e to the negative 0.04855 times 15. So plugging this into a calculator, we see that this is approximately 133 degrees Fahrenheit. So now looking at C, how long until coffee reaches 100 degrees Fahrenheit? So we're trying to find the time when this equals 100. So 70 plus 130 e to the negative 0.04855 t. So first, we're going to subtract 70 from both sides. So we get 30 equals 130 e to the negative 0.04855 t. And now we're going to divide both sides by 130. So we end up with 3/13 equals E 855 T. Take the natural log of both sides. Now we divide both sides by negative 0.04855. So we end up with T equals negative natural log 3/13 over 0.04855. And I like to put the negative in the numerator. Y'all could leave it in the denominator if you wanted. It's not a huge deal. And then T, plugging this into a calculator, is approximately 30.2 minutes. All right, so that is the end of chapter 4. So we will move on to chapter 10 after y'all's midterm.